No more boring problems. This buckling problem is a heist. Your TA Indiana stores his greatest treasure in the impenetrable fortress at the very top of the cat tower, which he knows Serenity can't get to because she's too fat.
What's he even hiding up there anyway? To have this level of security, it must be snacks.
So we're going to draw a slightly modified version of the cat tower here, and we're going to evaluate whether this cat tower can hold Serenity's weight in 3 different positions she'd have to climb to get all the way to the top. So at first she'll have to stand on a fixed column, then a pinned column will support her, and then lastly at the very top would be a fixed free column. So I start off by grabbing the equation from the FE reference manual for the critical force for buckling. So pi squared EI in the numerator, KL quantity squared in the denominator. So for this cat tower, all of these columns we're going to say are made of cardboard tubes with a Young's modulus of 60 KSI. So we've got the value for E already. The value for L is just the length of each column. So that's going to be 24 inches for the 2 vertical beams, and a little Pythagorean theorem here, about 1.4 feet for the diagonal support beam. And we're going to pretend that that's a tube also. So for K, I can also grab this from the equations in the FE reference manual. 0.5 for fixed, 1.0 pinned, 2.0 for fixed free. And I'm going to talk about what each of these mean when we go to actually solving each individual one. I'm just trying to gather what we know and what's still unknown so far. Looks like your TA Indiana wants to go check and make sure his treasure is still safe. So for I, the area moment of inertia, I'm actually going to the statics section of the FE reference manual to find this table for a ring. And so I can grab the equation here, IXC. So this is the area moment of inertia about the center of the ring, which is going to be based on these A and B. You can see are the outer radius and inner radius of the ring. So for us, the diameter is 2.75 inches with a ring thickness of 3/16 of an inch for this cardboard tube. So the outer radius, divide by 2, 1.375. Inner radius, take the outer radius minus the thickness, the 3/16. About 0.691 inches to the 4th. For I, area moment of inertia. So why is this bottom column 1 even fixed at all? Vertical columns in buildings are almost always treated as fixed because the floor prevents rotation, right? The floor and the ceiling. In order for the vertical column to bend at the joint, the whole floor would have to bend. But usually that does not happen. And so this is why these can usually be considered fixed. The floor, right, acts as a fixed joint to hold the column perfectly vertical. And the value for K then is very small for fixed joints. Again, because the edge can't rotate, it has to start vertical. For buckling to happen, it starts vertical before. It acts as if it is a much shorter beam. Effectively, the height gets cut in half, which is going to make it much more resistant to buckling. And now with Young's modulus known, area moment of inertia known, we can actually start plugging in numbers to solve this thing. So plug in all the numbers. 2,840 pounds. All right, this column is definitely not going to buckle under your TA Serenity's weight. But would it crush? Right, buckling's not the only failure mode. It might actually fail just do regular compression, like stress equals force divided by area. So now if we calculate the area for this ring-shaped cardboard tube, and then multiply that by the 232 PSI, the yield stress for cardboard that I found from, I don't know, ChatGPT or something. Now we're all the way down to 181 pounds that would cause this thing to break. And that sounds kind of reasonable for a cardboard tube. It's not going to necessarily hold up. This is designed for cats, not for people. But also you can see in this picture, there are like 4 of these. So it would be pretty robust. It's only when all of the weight is concentrated directly on top of one column that you'd really be risk of crushing just that one column entirely by itself. And the good news is we're not gonna have to recalculate this for every tube. The compression strength, since these tubes are all the same size, is gonna be exactly the same. So this 181 pounds is gonna be at the bottom and the cantilever and for the very top. It's all that same compression sort of crush strength in every scenario. We're only gonna have to recalculate the buckling strength. All right, so let's move to the cantilever next. Pinned joints are most commonly seen in trusses. Those members are always gonna be modeled as pinned. And so sometimes you'll need to consider buckling in a truss, not only tension or compression. So now with position 2, I'm using 1.0 for K and using my modified length here, about 17 inches. We still find that this isn't gonna buckle until there's 1,420 pounds. Now this diagonal beam will buckle at 1,420 pounds, but that doesn't mean that it'll break if Serenity weighs 1,420 pounds, because now in order for there to be 1,420 pounds in the diagonal beam, the downward force would actually only be equivalent to the vertical component of the 1,420 pounds. So if we take 1,420 times sine of 45 degrees, this is actually closer to only about 1,000 pounds of vertical force that would result in buckling. Of course, this is all still way above the 181 pounds that would result in it failing due to crushing. So again, buckling is not the major concern for case 2. Fixed free is most commonly seen for things attached only to the ground, like telephone poles or street lights or traffic signs. These can be really wobbly at the top because it's completely free. And so these are way more susceptible to buckling. They have a K value of 2.0, making it act as if it is a much longer beam. So when we plug in all the numbers, we actually get that this fixed free joint at the top of the cat tower is gonna buckle at 177 pounds, which is less than the crush strength. So of all the positions in the entire cat tower, the top position due to buckling is the place that would fail first. And so, moment of truth, does TA Serenity weigh more than 177 pounds? And sadly, I'm sorry, TA Serenity, look at the scale. It's not gonna hold you. You're not gonna be able to get the treasure.
Meow, I'm mad. Put me down immediately. Indiana can keep his stupid treasure. It's probably not even snacks anyway.
The real treasure are the friends we made along the way.
Aw, buddy, that is so sweet. If you thought this video was a little bit less boring than every other buckling video out there, go ahead and hit the thumbs up, and good luck on your next test.